Python with computational chemistry. And I guess we're aiming this at people who've maybe done a few calculations already. Maybe they're able to sort of fire up Gaussian and generate some transition states and ground states. But sort of this is what next? Some workflow tools that we've developed with Python. Did I get that right, guys? All right. Cool. So who's going to go first?
I can do mine.
Cool.
Mine's a bit longer, so we'll start with that one. Let me just try to share. I'm not sure. Hopefully the volume will work. It won't be like doubly through. But say something if you are having trouble hearing it.
Hi, my name is Julian. I am a grad student at Colorado State University working in the Payton Lab. And in this CCAS tutorial, I'm going to talk about how we use Python to compute some steric parameters. As a bit of an overview for today, I'm going to start off by talking about steric effects and how we can quantify molecular shape. Then I'm going to go into detail about a project in Python that we've been developing to obtain some steric parameters. Then I'm going to give a demo about this Python project. We often learn about steric effects in the context of steric repulsion in general in organic chemistry. In this example below, we have a cyclohexane with a methyl substituent in the axial position. The hydrogens on this methyl group don't want to be occupying the same region of space that these other axial hydrogens are occupying. And so that leads to this unfavorable interaction called steric repulsion. It would be more energetically favorable if this methyl group was in the equatorial position down here. But steric parameters attempt to describe the space that these sort of substituents or molecules are taking up. And we actually have the Winstein wholeness parameter, or A value, to describe the energy difference between an axial or an equatorial monosubstituted cyclohexane. Using experimentally observed equilibrium constants, we can describe the free energy difference between an axial versus an equatorial substituent. And we can see that with larger and larger substituents, we see larger and larger A values or larger and larger energy differences. So we saw in the previous slide that steric effects can influence things like energy differences, but they also have been known to influence reaction outcomes, such as percent yield or how fast a reaction is going to happen. The A value was a single dimensional parameter, meaning that it can be described just with one number. And a simple shape that we can describe with one number is a sphere. And so with a one-dimensional parameter, if we plug in our parameter as the radius of a sphere, we can basically describe molecules as spheres of different varying sizes. However, not all molecules are spherical in shape. Sometimes they look like this crazy thing on the right, in which case it helps to have a multi-dimensional parameter, or a parameter that we can represent with multiple numbers. In this case, we can measure different lengths or widths of our molecule and obtain more information on the shape of that molecule. And so with more complex molecular shape, it helps to have multi-dimensional descriptors or parameters, so that we can kind of describe these nuances that we aren't able to with a single dimensional parameter. So in this vein, we have developed a Python project called Dubstep, which stands for DFT-based steric parameters. And with this Python project, on the left-hand side, we can see that we can compute two of these more classical parameters, the first one being the Stereomul set of parameters. This was developed by Verloop in the 70s and then popularized by the Sigmund group lately. But the Stereomul set of parameters is a set of 3 parameters. The first one we measure along a bond axis usually. So along this boron-carbon bond, if we continue that axis until we reach the end of our molecule, this is known as the length or L parameter of our molecule. If we then look at this measurement from the top down, so down that L bond axis, we can then take 2 new measurements. One is the minimum width to that bond axis, and then the other is the maximum width to that bond axis, so Bmin and Bmax parameters. The next parameter that we can measure is the percent buried volume. This comes from Luigi Cavallo. This parameter describes in a metal ligand complex, if we place a sphere, typically we use a radius of 3.5 angstroms around that metal. We then measure how much of our ligand is actually occupying this sphere. And this tells us sort of how much of our ligand is occupying this sort of first coordination sphere of the metal. So we've taken these two more classical parameters and developed those a bit further to just get more information out of our molecules. And so that gives us these two parameters on the right, Stereomultivec and Multivec. The Stereomultivec parameter set takes the stereomul parameter set, and basically what we do is slice up our molecule along those the L axis, and we take new measurements of Bmin and Bmax along the length of our molecule. And so we're able to get information on how the width of our molecule, those minimum and maximum widths, both change as we sort of travel the length of our molecule. Similarly, we've expanded on the percent buried volume parameter by letting this radius of this sphere vary. We can then collect a parameter set from these spheres or hollow spheres, which again gives us information on how the occupancy of these spheres change as we go further and further from, say, a chemical point of interest. So in order to use this program, there are a few things that we need to provide the program. The first thing being reference atoms. So we need to look at our coordinate files and determine the index of specific atoms in that file. So if we're measuring stereomul parameters, we need 2 atoms as a reference. If you remember, we looked down a bond axis, so we need to define 2 atoms that make a bond in order to collect those parameters. And so in this case, I have this carboxylic acid with this orthotoluene group substituent. And if I wanted to know the stereomul parameters of this toluene substituent, what I would do is define this carboxylic carbon as my center atom, or my atom 1, and then this first toluene carbon as my atom 2, and then my measurement would take place from my atom 1 down my atom 2 until I reach the end of my molecule. If I was doing a volume measurement, all I would need is just 1 atom, since I would measure radially from a single atom. That brings us to the second thing we need to provide the program, which is which steric measurement we would like to measure. We can either do stereomul or volume measurements, or we can do both at the same time. If we'd like a 2-vec representation of these parameters, what we can do is add this scan interval. And so we provide the program with a start point, an end point, and then how frequent we would like those measurements in angstroms. We use this package called cclib to parse chemical input files or output files. And so this program allows us to compute steric measurements from all of these more popular quantum chemistry software output files, along with other common chemical coordinate files such as XYZ, SDF, or mol files. And if we're using this in a Python script itself, we can even import RDKit objects. Now that I've talked about kind of how to use this, let's jump into the demo. So now let's talk about how you would actually use dubstep to obtain some of those steric parameters. You can interact with the program in 2 ways. I'm going to talk about both of those today. The first being through the command line, so with something like a terminal on a Linux machine or Mac, or a command prompt if you're using Windows. And then you can also interact with this program through Python, just using a script itself and importing the module. So first I'm going to talk about using the command line. In this folder, you'll see I have this log file, and I'm going to go ahead and open that up in Gauss View. And we can see that it's the same molecule I was talking about on that last slide. It is this orthotoluene group on this carboxylic acid. And I'm going to go ahead and measure the stereomul parameters of this toluene substituent. I'm going to, like I did on that last slide, define my carbon 1 as this carboxylic acid carbon, and then my carbon 2 as this first toluene carbon. I'm going to measure my stereomol parameters through that bond axis until I reach the end of my molecule. So I'm going to start off by typing python-m db step, and then I'm going to provide the program with that output file. I'm going to then define those reference atoms. So atom 1 is going to be that carboxylic acid carbon. I don't know if this is too small to see, but Gauss view tells me that this is carbon 8 in my file, and so I'm going to define that as 8. And then atom 2, this program tells me is carbon 7. Now, since I'm measuring steric parameters of this substituent, I don't really want to get any of the sterics for some of these other oxygen and this hydrogen atoms. So what I can do is actually provide a new argument called exclude, and exclude these 3 atoms from any steric calculations. And so Gauss view is telling me that these atom indices are 9, 10, and 18. So I'm going to provide this exclude argument to the program and say 9, 10, 18 are the atoms I don't want any measurements on. The last thing I need is the type of steric measurement that I'm going to input to the program, and that is going to be Stereomul. So I'm going to go ahead and submit that, close this window. And we can see that I get back my Stereomul parameters for this molecule. My Bmin is going to be 1.77 angstroms. My Bmax is 4.43 angstroms, and then that length is 6.4 angstroms. These numbers are nice to look at, but it's even nicer to get a cool visualization, and luckily Dubstep will output 2 new files that help in just doing that. And so the first is this XYZ file, which is just the coordinates of my molecule, and then the next is a Python file which helps to display these in a program called Pymol. So I'm going to go ahead and open this XYZ file in Pymol, and we can see that our molecule is present. It's the same molecule minus those 2 oxygen atoms and that hydrogen. If I then type run in this Pymol window and add in this Python file, what I get is these axes showing me my Stereomul parameters. And so the longest axis that is being displayed is my L parameter. So this blue one shows me down this carbon-carbon bond that I defined. I see an axis of 6.4 angstroms, and you can see that goes down to the end of my molecule. If I look at this down that bond axis, I get my my width parameters. And so I see my Bmin is this smaller one at 1.77 angstroms, and then my larger width, my Bmax, is 4.43 angstroms going off that toluene loop. So this is nice, this is good overall parameters, but what happens if I want those Stereomultivec parameters? If I want to measure more proximal sterics from this, down this carbon-carbon bond? I'm going to actually type in that same command that I had done earlier, and then add the scan argument. And so I'm going to look at how the sterics change within the first 3 angstroms down that L axis. And so I'm going to start off with 0 angstroms. I'm going to measure until I hit 3. And then I want a new measurement every half angstrom. So I'm going to go ahead and submit that calculation. And I'm going to start getting output. And my R value tells me how far along from 0 to 3 I am. You can see I'm getting new Bmin and Bmax measurements as I scan down that length axis until I reach R of 3.0. And it even tells me my L parameter at the end. It matches what I had previously. And so I've overwritten my previous output files with new ones. And I'm going to actually just reopen them. We can see that the output is the same. I have excluded my oxygen atoms still, but I'm going to rerun that Python file, and what you'll see is I get these new axes every half angstrom as I scan down along this L-axis. And so I'm going from 0 angstroms down to 3 angstroms, and we can see how those sterics are changing because of this methyl group. This gives us, again, more proximal sterics, different information, new information from what we were receiving from just the overall stereomul parameters. So now that we've seen how to use dubstep on the command line, let's see how it works in a Python script. So I've switched directories into a new folder called Python, and inside this folder I have an SDF file which contains coordinates for this triphenylphosphine and a Python file. So let's go ahead and open this SDF file again in PyMol. We can see that I do indeed have this triphenylphosphine, and on this ligand I'm going to measure the Multivec parameter sets. So I'm going to measure the buried volume in sort of an interval radially from this phosphorus atom. And I could input this and measure the stereomul parameters as a sort of tridentate ligand, but instead I'm just going to measure the volume, so I only need one reference atom, and in this case it's going to be this phosphorus. So let's go ahead and open up this Python script and kind of talk a bit through it. So I'm going to import dubstep, and I'm also going to import RDKit. Let's say if I had a bunch of these different phosphine ligands and I didn't really have consistent numbering throughout, I don't know exactly which index the atom, the phosphorus atom, is in each of those files. What I'm going to do is use this module called RDKit to go through and identify the phosphorus in this file. And I could do that through a series of files, but since I only have this one, we're just going to use this one to start off. So I'm defining my file as this SDF file. My base group that I'm going to look for the index for is this phosphorus. And then the scan interval, which I'm going to run this Multivec parameter set, is going to be from 0 to 8 angstroms, and I'm going to measure every 2 angstroms. And so without going through this line by line, basically what I'm going to do is open up my file, search through the atoms for this phosphorus, and then I'm going to print out some useful information along the way, such as if I found that phosphorus atom, what index is it, and then I'm going to submit that information to dubstep. And I'm going to provide it just with my RDKit mol object, which we'll grab the coordinates from. And then my atom 1 is going to be that phosphorus index, which I've identified earlier. I don't need an atom 2 again because I'm not measuring any stereomul parameters. I'm going to tell it that I want some volume parameters, and then I'm going to pass that scan interval of 0 to 8 angstroms every 2 angstroms. And what's nice about using this in a Python script is that I can access these parameters afterwards, since I've stored them in this steric object. And so I can see that I'm going to access this buried shell value, but I could do this with any of the parameters measured. And what's nice, I could store those in a data frame or a CSV file. I could export those, or I could just do some statistics in Python right away. But for now, let's go ahead and run this script and see what we get out. So I'm just going to type in Python Multivec and give it a go. And so right away, we've identified our phosphorus as atom 1 in our SDF file. And then it's going to go through and submit that to dubstep. And we can see we get kind of similar output, a bit different, but we are doing those radial scans. So at 0 angstroms and then 2, 4, 6, and 8 until we've reached our end. We get % buried volume and also % shell buried volume. And so every single step along the way, we get a new value for those because we're scanning out radially from that phosphorus atom. And then we can see that I can access those parameters afterwards. What I've done and what I showed earlier is that I was going to print out the third value for my buried shell, and that's exactly what I've done. I have my % buried shell volume as 26.47. Here I've printed out with greater accuracy 26.468. It's also a nice part about using this in a Python script is we don't just get what's printed out to the terminal, we can access more of these numbers. And the accuracy of these numbers kind of depends on the spacing. So we use, when we're measuring volume and stereomul parameters, a grid to kind of measure and count up voxels of that grid of which states are occupied and which are not occupied. And we can actually change how close together those grid points are and get more accurate values depending on how accurate we need to be and depending on the computational resources that we have. And so this is how you would use this in a Python script. Thank you guys for watching. Hopefully you've learned a bit about different ways we can collect some steric parameters. Check out our website and our Twitter for up-to-date information on the center, and then our GitHub for future code releases.
That's what I got for you.
Good.
Feedback.